polynomials. And then after that, I'm also going to show you how you can use long division of polynomials. But first, quick review of long division. So if you're doing 8 divided by 3, we all know that's 2 2/3. But let's say you didn't know. You could use long division to find out what it is. So you ask yourself, how many times does 3 go into 8? How many full 3's go into 8? And that would be 2. And then 2 times 3 is 6. You put that under the 8, and then you subtract because you want to know how much you have left. You have 2. And that's it. So you're going to have a remainder of 2. And that means after you've taken away 6 from 8, you really have 2/3 of a whole left. So you have 2/3 of a whole. So 2 3's and 2/3 of a whole is equivalent to 8 divided by 3. Now, this isn't a weird way to write your answer, so we would write this in a mixed number form. So 8 divided by 3 is equivalent to 2 2/3. Okay, so that's your quick review of long division using just a fraction of 2 integers. So now we're going to do long division with polynomials. So I'm going to do 3x cubed minus 2x squared minus 13x plus 14 divided by x minus 2. So this goes inside that structure. And x minus 2 goes on the outside. So now I'm going to ask myself, how many x minus 2's fit into the first 2 terms of that polynomial? How many x minus 2's fit into those first 2 terms? So what times x minus 2 gets me as close to 3x to the third minus 2x squared as possible? So I'm going to focus on the x, the first term in the divisor, and the 3x cubed, the first term in the dividend. And I can get exactly 3x cubed if I multiply the x by 3x squared. So that's what I'm going to do. 3x squared times this entire binomial, x minus 2, gives me 3x cubed minus 6x squared. Okay, now I subtract. Now here, since I have 2 terms here that I'm subtracting from these 2 terms here, there's a potential of making a mistake when I'm doing the subtraction because I got negative signs here. So I recommend that you put parentheses here to help you remember to distribute the minus sign, this minus sign. So negative 2x squared, negative 2x squared minus negative 6x squared is negative 2 plus 6x squared. So that's positive 4x squared. And then this will be 0, so I don't have to worry about that. I'll just do that. And then I bring down the next. If I were doing long division with integers, that's what I would do, right? I would go like this, subtract, and I would bring down the next digit. So that's what I'm going to do here. Except these aren't digits, these are terms. So I have to bring down the next term, which is a negative 13x, so minus 13x. And I do it all over again. How many times does x minus 2 go into 4x squared minus 13x? And again, I focus on the first terms, the x here and the 4x squared here. So I can get exactly 4x squared if I multiply by 4x. And 4x times x minus 2 is 4x squared minus 8x. And then I subtract. I'm going to put parentheses here to safeguard against any mistakes. And I get negative 5x. Then I bring down the next term, but plus 14 this time. And I do it one more time. How many times does x minus 2 go into negative 5x plus 14? Negative 5 times. And negative 5 times negative 2 is positive 10. And then I subtract. And I get 4. There's nothing more to bring down, so I'm done with the dividing part. I have a remainder of 4. So what do I do with that? Well, let me remind you, when we do it with integers, when I have the remainder, I add the remainder over the divisor to whatever the quotient is. Okay, remainder over divisor. That's how I get the 2/3, which eventually becomes this 2/3 part of the 2 2/3 in the end. So that's what I will do here, remainder over divisor. And I will put plus. I can't use the shorthand like I do for the mixed number here. I can't just write after the 5, 4 over x minus 2, because it'll look like 5 times 4x minus 2 if I do that. That's fine when you're working with just integers here, because everybody knows 2 followed by a 2/3 means 2 plus 2/3. Everybody knows that. But if I do that here, the reader is unsure. Does this mean 5 plus 4 over x minus 2, or does it mean 5 times? We don't know. So I put the plus there so it's clear. And so this is what you get when you divide that 4-term degree 3 polynomial by that little binomial. Okay, I'm going to do this again with a different, with 2 different polynomials, because there's a little wrinkle in this one. Okay, so I'm doing x squared minus 5x plus 7 divided by x plus 1. Okay, so I focus on the first 2 terms, the first term here and the first term here. X goes into x squared x times. Then I multiply. Then I subtract. Bring down to 7 plus 7. I do it again. And I get 14 remainder. Remainder over divisor plus remainder over divisor. And there you go. Actually, that wasn't the one I wanted to show you because that had no wrinkle. This is the one I wanted to show you that does have the wrinkle. It's a binomial divided by a binomial, but the dividend is a higher degree, so that's why I can do the long division. I'm going to write the x plus 2 out here first. Now, when I write the x cubed plus 8 in here, I am going to put placeholders in between the x cubed and the 8. So here I have a placeholder for x squared, 0x squared, and for x, 0x, followed by the plus 8. Now why do I do that? Well, let's say you were doing 2008 divided by 7. You're going to write 2008 divided by 7 here. You will not write 28 divided by 7 because that's a totally different problem. Now, that's not to say that if I didn't write the 0x squared and the 0x, that I would have a totally different problem. I actually wouldn't. But it's going to help keep things organized, because when you're dividing, when you're long dividing with polynomials, it's really important that we keep the columns in order, because this is the x cubed column, this is the x squared column, this is the x column, and this is the x to the 0 power, or the constant column. And if I don't have those placeholders, I might forget the order of the columns, the powers of x. And I think you'll see the advantage of this when I start doing the division. Okay, so here we go. X goes into x cubed, x squared times x plus 2 is x cubed plus 2x squared. And now I do the subtraction. And here's where the columns help. Imagine if that 0x squared had not been there. I'll put my thumb over it. It's not there. And now you're doing subtraction. Okay, x cubed minus x cubed, no problem, that's 0. But what are you subtracting 2x squared from? Okay, maybe you can remember that you're subtracting it from 0x squareds. There are no x squareds, so 0x squareds in the dividend. But if you don't remember that, you might get stuck there. So, but if you see the 0x squared there staring at you, then you know for sure, oh, I'm doing 0x squared minus 2x squared, which is negative 2x squared. So that's why I highly advise that you actually write the 0x squared there. And then I bring down 0x. Now that may sound silly, but you'll see that in the second cycle, you'll see why I did that. Okay, then x goes into negative 2x squared, negative 2x times. Then I multiply. And then I subtract. And you see the 0x is useful here, because now I see that I'm doing 0x minus negative 4x, which is 4x. Then I bring down the plus 8. And then last time, 4 times x plus 2 is 4x plus 8, and there's no remainder. So I don't have to worry about adding something, tacking on something here, plus some fraction. It factors, I mean, it divides evenly. All right, now I'm going to talk about the usefulness of long division in graphing a specific type of function. So what we're going to graph, or what we're going to divide, is a trinomial by a binomial, kind of like the one we did here. And we are going to get a remainder. And then we're going to do something with that remainder, and then we're going to graph the original function. Okay, so I'm going to make up one here and hope this works. We're going to do x squared minus 3x plus 8 divided by, let's go with x plus 2. Okay, so keep in mind that the function is x squared minus 3x plus 8 divided by x plus 2. Okay, this is our original function. I'm going to actually divide the top by the bottom and see what we get. Subtracting for the first time. And then minus 5. And then subtracting second cycle. And I get a remainder of 18, so plus 18 over x plus 2. Okay, now I'm going to talk about what the graph of this function looks like. So a couple of concepts first. The concept of asymptote. So in some functions, when you plug in a very large x number, and I'm talking very large, either very large positive or very large negative x value, the y value of the function gets closer to a certain value, but never reaches that value. And here's an example. This simple function, f of x equals 1 over x. When x gets really large, like 1/100th, or 1 over 1,000, or 1 over a million, you'll see, when x gets to 100,000 or a million, you'll see that the value of the whole function, 1 over x, it's getting really close to 0. The larger number I put in for x, the closer the function gets to 0. But since we have a 1 in the numerator, the overall function will never actually be 0. Never be 0. Well, what about negative numbers? If I put in negative 100, or negative 1,000, or negative a million, the overall function is still getting close to 0. So the function is looking like this. As x gets big, the y values approach 0. As x gets very negative, the y values approach 0. But they will never cross the x-axis because of that 1 in the numerator. So I'm going to draw a dotted line here. This is an asymptote that shows you what the boundary is for the y values of this function. It never crosses 0. So y equals 0 is that boundary, and we call that the asymptote. There is also a boundary here, a vertical asymptote, because, looking at this fraction, x is not allowed to be 0 because you can't take 1 and divide it by 0. So there's another boundary, another asymptote here. And as x gets small, the overall function gets big, because what if I put in something very small in the denominator, like 1 over 1/10? You get 10. 1 over 100. You get 100. 1 over a million. You get a million. So the function is getting large very quickly as x gets small. So here's x getting small, 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 and y is climbing. Same thing will happen if you put in negative small values for x. X gets small, 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 and then y becomes a very large negative number. Just put negatives in front of here. You're going to get large negative numbers. And so this function looks like this. It's called a hyperbola, but the name of it's not important now. I just want you to see how the x and y values interact and how the function behaves at large x values. Okay, so now back to the function in question, which was this, which we found is the same as this. Now I want you to focus on this fraction here. This fraction behaves in the same way that this fraction behaves when x is large. And what I mean is, when I put a large number in for x, in the x plus 2, in the denominator of this fraction, 18 over x plus 2, what happens to the denominator? It gets large also. And if I put really large numbers in for x, x plus 2 gets really large, much, much larger than 18, which can't change, it's constant. So when I put very large values of x into the denominator of this fraction, guess what? That fraction also approaches 0 in the same way this fraction approached 0 when x is large. Okay, so if this fraction is approaching 0 when x gets very large, then this whole expression is approaching x plus 5. Because this fraction is going to disappear as x gets big. And then what's left? X minus 5. Yes, x minus 5 is a very large number because I'm putting a very large number here for x, and therefore I have to put it here as well. But we do, another thing we know about x minus 5, in addition to it being a large number, is that this is a line. Remember y equals mx plus b? This is a straight line with a slope of 1 and a y-intercept of -5. In other words, this is the boundary. This is the boundary that this function doesn't cross when x gets very large, in the same way that this was a boundary, y equals 0, when x gets very large. The difference between this boundary, x minus 5, and this boundary here, y equals 0, is that this is not a horizontal line. As I just mentioned, it has a slope of 1, so it's not horizontal. It is a diagonal line with a slope of 1 and a y-intercept of -5. And I'll label it here. So this is the asymptote for this function, the diagonal line y equals x minus 5. Okay, what about that other asymptote? Okay, that one is simpler to find. Remember that we can't divide by 0, so the other asymptote is x equals -2, because x is not allowed to be -2. So this is the other boundary, and that's a vertical line that mimics the... Oh, sorry, it's not there. It's at x equals -2, so over here. X equals -2. So we've got two boundaries, a vertical one and a diagonal one for this function. And I'm going to leave off the graphing part for the actual function for another video. But this is how you get the asymptotes for a function that has one vertical one and one diagonal one using long division. Okay, see you later.